Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, March 26th, 2021. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a balmy spring evening in Rockport, Massachusetts. These Earth and Space Reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about the life-sustaining environment of our home planet, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. Today, we are joined by members of the Rockport Research Explorers, Rockport Cultural Council, Gloucester Area Astronomy Club, and other curious folk. So thank you for coming. Our special guest for this evening is Dr. Enrique Lopez Rodriguez. Enrique is a research scientist at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. He is originally from the Canary Islands of Spain, where he earned his bachelor's and master's degrees at the University of La Laguna in 2008. He then moved to the United States, where he obtained his PhD at the University of Florida in 2013. He next worked as an assistant professor of research at the University of Texas in San Antonio, then as a research fellow at the University of Texas in Austin, and as a visiting postdoctoral scientist at the Sofia Science Center in California, before his appointment as instrument scientist for the Hawk Plus camera aboard Sofia. Along the way, he has held visiting research positions at the National Astronomical Observatory of Japan, at the University of Tokyo in Japan, and at the University of Utrecht in the Netherlands. This evening, Enrique will be talking on galaxy magnetism as revealed by Sofia, the Stratospheric Observatory for Infrared Astronomy. So Enrique, welcome to our little gathering.
Well, yeah, thank you, Bill, and thank you for the lovely introduction and naming every single place that I've been moving. So I think I've been moving around, and I will share the reasoning behind that. And thank you for inviting me to show the results with Sofia, which I will show what Sofia is and what do we put a telescope in the back of a Boeing 747 and what kind of science we do with it. So I'm gonna try to do it very informal. So if in the middle of the talk you have any questions or you want to comment something, feel free to do it. Let me see if I can share the screen right now. Okay. Can you see it?
Yes.
Oh, excellent. Perfect. So here, so what I'm gonna show is some of the latest results that we have obtained with Stratospheric Observatory for Infrared Astronomy, or we call Sofia. Here I show some of the images around the slide, and I will go in detail later what all this image means. So I think that what Bill say, I'm from Canary Islands. I don't know if you know where is it, but these tiny islands very close to Africa, to Morocco here. And if you zoom in, you have the 7 islands. And I'm from this city called San Cristobal de la Laguna. And this is what the islands look like. You have a volcano, which is the tallest point in Spain. And we have some snow once in a while. But the rest of the year is more or less very shiny. So I don't have to explain every place that I've been, but I think what I want to say here is like moving away from my hometown was one of the best experience that I ever have in my life. It's not only just to experience living in another place and being more independent, but also learning the culture from other places and also learning about my own land, because people in, for example, in Austin, like, oh, tell me the story about the Canary Islands. And like, oh, right, now I need to remember all that. So I need to just like remember all and actually learn more about it. For example, in San Antonio, I didn't know that San Antonio was founded by Canarian people, for example. I didn't know about that. And then you have like 14 families from the Canary Islands travel to this part of Texas and create San Antonio that we know now. Also, you have new languages, for example, a little bit of Japanese and a little bit of Dutch too. So, but the most important part is that I follow all the good weather song all the time, or what I call the Enrique habitable song. So, you know, the astronomers are always looking for planets to live and looking for the specific area to live from. I don't want to go to the Utrecht again, even though it's very lovely, but it's very cold for me. So if you have any questions later about all the path for astronomy, let me know and we'll be happy to talk about it. But let's focus on science. Let me start with the whole picture of the universe here. So if we were able to take a picture of the universe, it should look like something like this. So what you have is a lot of clusters of galaxies, which is like all these points that you see here. It represents a galaxy, and they're all grouped in clusters. And then like whatever you look at, so it should look more or less the same. So that means that the matter is distributed more or less homogeneous in the universe, and there are no centers, no edges anywhere. So when you look at this picture, this is all simulations, okay? So all these images that you see there was created due to gravity. What you have is at the beginning of the universe, you have the homogeneous distribution of matter, and then because of gravity, they start collapsing, is what you see here in these data points. Every single data point that you see here is represent a galaxy. And then galaxies start collapsing and creating bigger and bigger galaxies and bigger groups. So then this area has more gravity than this part here. So then all these galaxies that you see here getting more attractive to this cluster of galaxies. So for that reason, you create these very big filaments of galaxies and moving around them. This is a combination of gravity and something that we call dark matter too. So if you look at this video, but in a different way, so what we represent here is the beginning of the universe here, the Big Bang, and then you have expansion of the universe, and then after a few after all this matter collapse and create the first protons and matter in general, so you start creating the first stars, and this is what you represent here. So after all those stars and galaxies form, you will start forming small galaxies until you see today. So here the main point is like we are here right now, and if we look to further away galaxies, what we're looking is two different things. You look galaxies, they're further away, and you look galaxies that are not as they are right now, because the light has a finite travel time. So then it will take, in this case, like a few billion years to travel. So so every single picture that we take is actually a picture of the past as they look in the past. So just a snapshot of the simulation I see before. If you zoom in one of these clusters, what you see is one galaxy. So, and this is like the typical galaxy. Here is like every point in this case represent a star. So you have a accumulation of stars moving around the center of the galaxy that we think contains a black hole in the center. So if we zoom in one of those galaxies, for example, the Milky Way, this is what it should look like. You have galaxies of typical diameter, for example, of 125,000 light years. And you have the center of the galaxy, but very bright, with a lot of accumulation of stars, and plus the black hole in the center. And then you have something that we call the bar, and then you have these spiral arms moving spiraling around the center. So we know that the Milky Way is around 13.2 billion years old. And as I said before, every single point here represents a star. We know that our galaxy has around 200 to 400 billion stars, where some of them has planets, and some of those planets are maybe supporting life. So if you zoom in, for example, in this area that we think is where our planet is, you have the solar system, which is a single star with a bunch of planets, and then we have our planet on it. So I think now you have the whole picture from the whole universe to now, to our scale in the planet. But what I want to focus is in the full picture of a galaxy. So you know exactly when I talk about a galaxy, it's accumulation of billions of stars and dust and gas moving around a supermassive black hole in the center. So what I say before is all simulations, it's all pictures, but let's go and observe some galaxies here. So for that, we use, for example, the Hubble Space Telescope. It's a 2.5 meter telescope in space. So this is one of the picture here. And what Hubble did is one of the most impressive pictures that it has. It was like the Hubble telescope observed one point of the sky for 1 billion seconds, which is like correspond to 11.3 days. The idea of this was that the director of Hubble say, I want to have the picture with the deepest galaxy ever seen before. And then what he observed is, so it's this part, for example. So what I show here in this is a picture of the constellation called the Big Dipper. So, and this tiny thing here is like if you put a penny on the sky, this part of the sky, you zoom in and you zoom in again and you zoom in again, you start seeing thousands of stars in a very tiny space of the sky. So, and that was like astonishing just to see all these galaxies here. So, and as I said before, these galaxies we are not seeing as we are now. So yeah, we're seeing as it were in the past. And you see them, some of them collapsing, some of them no, and you see some of these galaxies are very, very faint and very far away, and some of them are very bright and very close. So in this case, every point that you see here is an individual galaxy. They're not stars. So they're all related with outside of our galaxy. So if we zoom in this picture, you start seeing different type of galaxies. You see some galaxies that are spiral, like ours. You see some galaxies that are elliptical. So in this case, they don't have spirals there. So you may have a supermassive black hole in the center, but maybe this has been after interaction with several galaxies, you have this very bright galaxy and halo around, and you have some of them that have no shape at all. So you have these regular galaxies, or maybe interacting. So if we took a picture and compare the size of the galaxy, this is something that you see here. You see this one, for example, this is an elliptical galaxy. As I said before, you have some of them are spiral, but you have some of them are very curious. You have a one in the center that looks like a spiral, but you have these humongous jets of, so the center of the galaxy has a black hole that is expelling matter very high velocities, and creating these huge ejections of matter that we call jets into the intergalactic medium. So it's the medium between galaxies. And you see some galaxies that are very, very small ones too, which is this one, for example, the Sombrero galaxy. So now I have a question actually. So which one of these is the Milky Way? I don't know if somebody want to even say something here. I have a number here. I don't know if you are very brave to say something about it. Which one do you think is the Milky Way there? I'm gonna give you 10 seconds. Or maybe in the chat if you want to say something.
18.
11, 3, 18. Okay. So, all right, I think we have one person that knew how to do it. Okay, 18. Well, the one is actually the 11. It's the most like simplistic galaxy in all these sample here. You see, like it's nothing actually special in our galaxy. It's a very typical spiral galaxy, very late and very organized. So, but you see some of them that are more interacting, right? And this one has these tidal effects here. So now let's go and see what the components of the galaxy has. So as I said before, you have a galaxy here in the center that we call the bulge. And this bulge is accumulation of a lot of stars and also the supermassive black hole in the center. Some of them has these spiral arms, and then the spiral arms are inside of the disk. And then outside of the galaxy, whatever is around the galaxy is this part here. For example, that looks very bright, we call it the halo. And then you have this accumulation of stars that we call global clusters that are more or less outside of the disk. The disk is composed of stars of all ages and has a lot of clouds of gas that may collapse and create new stars. And you have this spherical component that we call the halo that usually have very old stars and is no gas at all there, because usually the gas are concentrated in this disk in the rotating disk of the galaxy. So now, let's go, now that we know about the galaxies, and I showed you the example of one telescope that has observed the deepest image of the galaxy. So let's see what other observatories are there. So you know that we have ground-based telescopes. Those are telescopes on the ground, but they're only visible, so they can only observe a specific part of the electromagnetic wave. For example, we have the optical window here. They're mainly most of the telescopes that you see in the mountains are observing the light that our eyes can see. For that reason, we call it visible. But we also have antennas that observe radio wavelengths. Mostly what we have done in astronomy is we are not able to observe anything in the infrared or X-ray. So we send telescopes to space, and we call it space-based telescopes. The Hubble Space Telescope is the one that I showed before. Is another window, the same as the optical window in our on the ground, but because we don't have atmosphere, so the images are usually are more has a better resolution than these ones and than the ground. And then you have the infrared, for example, you have something called Spitzer or Herschel that try to estimate the to take images of the temperature of objects, and then you have X-ray and gamma rays. But the space-based telescope has an issue. So they are very expensive. For example, the James Webb telescope, they're going to be launched this year. It costs $7 billion. And they normally take a few decades to do it. And it's technology that need to be proved and need to be worked correctly, because you don't want to send something to space that break because you cannot go there and fix it. So, and usually have very old technology. For example, this James Webb telescope, the camera are already 15 years old. So we're sending something this year that it looks new, but the cameras are already like 2 decades old cameras. So whatever camera you have right now is much better than the cameras that are going to be in space. But it's going to be much better than the cameras from space telescope, which are 50 years old already, right? So what is the alternative here? So, well, the alternative is put telescope in the back of a 0.747 and be in the middle between the ground and space. And there's something that we call stratospheric observatories. So what is Sofia? So Sofia is the Stratospheric Observatory for infrared astronomy. And this, what it tried to do is to observe the infrared universe, which is trying to estimate, trying to get the images of the temperature of the objects, basically. And what we have here is a 100, more or less 106 inches telescope here in the back. Usually we have like 7 instruments. The newest one is the one that was working, the Hawk Plus, which I will explain a little bit later. And then we usually fly 560 miles per hour, and we observe at the altitude of between 37,000 to 45,000 feet. So the regular commercial fly for a Boeing 747 is 40,000 feet or so. So we are a little bit higher than the regular commercial flight. And the amount of people that we have there, we have 3 pilots, We have the mission crew is the safety people, for example. So we have 2 to 6 people, and also the people who control the instruments, the people who control the telescope. So they're like 2 to 6. The scientists are the people who look at the data and make sure that the data is taken correctly. It's between 1 to 3 people. And the educators is like we open once or twice a year a call for high school teachers to come and fly with us. Just experience how is taking images with a telescope in an airplane. We usually fly 8 to 10 hours overnight. So just inside of the inside of the airplane is something like this. So what you have is you have the telescope in the back, and then you have 2 different floors. So the upper deck is where you have the pilots. They have their own room and their own rest seats here. And usually you have 3 pilots on the top, and then at the bottom is where the rest of the 10 people sits. So you have the education panel here on the back, and then you have all the scientists here. And then you see that the telescope is separated from the cabin. So we are pressurized, it's like a regular flight of Boeing 747, but the telescope is not. The telescope is whatever pressure or temperature is outside. And you have a door that opens when we are at 37,000 feet. So this door opens and there's nothing here. So it's not a glass or anything. It's like completely at the atmosphere. So if you look at this area and at this wall here, is this image that I show here, right? So this is the telescope. So the primary mirror is this mirror here, is the one that observes the light. And then this light is reflected to a secondary mirror here in this part, and then reflected to a third mirror again, and then send it to us, to this instrument that is here. And you can see that send it through the pressure bulkhead that separates the cabin from the telescope. So this cabin here, I will show a little bit how it looks like, but it separates something that's pressurized that is unpressurized. And also it absorbs all the vibration of the instrument, of the telescope. So what the Boeing 747 looks like? Well, the typical one looks like this, very crowded. As you remember to fly those days years ago, and very crowded with hundreds of people inside. But the Boeing 747 for Sofia looks something like that. So it's only for 10 people and full of instrumentation, and not as beautiful as well, not as crowded as the other one. So what you have, what you see here is this part here. So so this picture is taken from this area of the airplane and looking back to the tail. All right, so what you can see here is like 3 people usually sitting here controlling the instrument, another 2 or 3 people sitting here controlling the telescope, and this is the telescope here and the instrument. So the telescope is in the back, right? So of this wall. And so let me go and zoom in this area and show you something very interesting here. So this is the wall that separates the telescope. All right. And this is the cabin where it's pressurized. So the telescope, it should look like something like these red lines, but in the back. So if you have flight before, you know that it's a lot of vibrations there, and sometimes it's even very complicated to drink water from it. So how do we control that the telescope is pointing to the same place all the time, and we are not having the stars or whatever moving around the camera? So, and this is where all this bulkhead comes out. You see this blue ring here. This is a mechanical mechanism that absorbs the vibration of the telescope and try to stabilize it. So here, what I'm gonna show you is a video that what I have been doing is in my computer. What I made is like I make this the telescope to be stabilized, and you will see how the vibration of the telescope of the airplane move. And this is something that you will see during the night, right? So you see that the airplane is moving around all the time, but this bulkhead is absorbing the vibration and making the telescope to be fixed to a position of the sky all the time. So then it's looking at the same star without any movement there, right? This is all German engineering here. Yeah. Yeah, so this we have this all the night. So you have that is working, so it's two systems, right? So one is like all mechanical, and then we have a guiding system later that we are forcing the telescope to look at the same time. But this is like this blue ring, the bullhead is doing all the mechanical work here. So what the flight looks like. So here, what I show is a very special flight from a few years ago. I need to tell you that Sofia is in Palmdale. So Palmdale is outside of Los Angeles. So it usually is what it is, like 45 minutes east from Los Angeles in the desert. And there is a NASA base, is the Armstrong Research Space Base, where the telescope is usually there for most of the year. Sometimes we go to New Zealand. And a few months ago, the airplane was in Germany for 2 months for repair and also for doing science flights there. So here you see when you recognize the US. And what I show here is this path is the path that we do in one night, for example, of observation. So what I show here, all these numbers, is every single object that we observe every night. So for example, we observe the Orion, or we can observe some nebula. We observe some calibrator to calibrate our instrument. And here in this graph, you see the altitude. Okay, so the 0 is the ground level, and this is 45,000 feet. And you will see how the airplane move up and move down depending of the flight. So if you start the night, and this is the time, right? So you see like 20 minutes, 30 minutes, 30 minutes, 40 minutes. You see that within the first hour, we do a very fast climb from 0 to 38,000 feet. And then we climb a little bit more, and then we start doing the observation. So every single straight path that you see here, we call it a leg. And every single straight path is one specific observation. And you see that the sky move, and then the telescope is only in one side of the airplane. So if one scientist want to observe Orion, so we need to point the telescope there, and the airplane also to that direction. But if another scientists want to observe a galaxy that is in another part of the sky, you need to physically move the whole airplane to the other side and then start observing again, right? And so then for that reason, you have all these paths here, right? And then that what you do is we observe, so you take 1 hour to go up 38,000 feet, and you see that in order to go higher, you need to take more time because you have to burn the fuel because the airplane is very heavy at the beginning of the night. So you cannot go to 45,000 feet all the way from the beginning because the airplane is very heavy there. So you need to wait and start burning all the fuel that we have. Well, most of them, and then whenever we are lighter, we can go higher and higher and higher, right? Until 8 hours of observation, and then we come back an hour down, and then we come back to Palmdale afterwards. So how the flight plan looks like, and then this is interesting here. You can see these kind of plans online. So this line here, this dot line, is the West Coast, right? So you can recognize California here, this part, this part, this part. So this is California. This black dot here is Los Angeles. This part here, the South Bay, San Francisco, and you have Baja California, and you have the Pacific here, right? So these black lines are the way up and the way down, and the blue lines is every single observation for different objects, right? So sometimes we go to the Pacific, and here in this case, we went all the way to the East Coast and then come back again because this is what the the scientists want to do. And the interesting part here is like all these green boxes, they're all military zones. So we cannot fly everywhere we want. We need to, so the airspace is controlled by the military too. So as you see here, we are not allowed to fly here, but we are allowed to fly here in this case. And we are not allowed to fly in these areas too. So what we do is like whatever the scientists want, we need to also move around these areas also too. So all this is public. It's no bad to show any of this. So, and the interesting part here is like if you go, so every single commercial flight, which I didn't know when I joined Sofia, and it's coming, for example, from Asia, from the west and going into Los Angeles, need to go through this corridor here. And this corridor is only a corridor of 350 miles. So every single airplane that go to LA need to go through this, which I didn't know there. So you have thousands of airplanes going there every single day, going up and down here. It's very curious. So let me go and then show you what do I do with Sofia. So I show you what I do. So what Sofia is. So I'm basically interested in magnetic fields. The magnetic fields are produced by difference of electric charges. So the typical example for all high school students is to have a magnet and to throw around iron pieces, and then you see that they're not randomly distributed. What you see is this distribution of lines around, right? So you can see you have a positive and a negative, or north or south, and then you see that the iron pieces are kind of like connecting in lines around. And this is what we call the magnetic field lines, right? And this is produced because you have iron, for example, in particles, and then they need to be oriented a specific pair in a specific regions. So in this case, what we do there is to take pictures of galaxies, and we are not able to observe these lines directly, but we need to do is observe what the magnetic fields do to the matter itself. So as you can see here in this particle here, you see that they're all aligned around these magnetic field lines. So, and this is the how's it called? The feature or the signature in galaxies that we want to see. We are looking at particles, and if you have magnetic fields, and if those magnetic fields are strong enough, you should see these particles oriented in this with this signature here between this north and south, or positive and negative. And this is what we see here, for example, in spiral galaxies. As you can see there, so the spiral galaxy, as I said before, so every data point is a different star, and then you have gas. And what I show on top of it, these lines, and these lines are the magnetic field lines. This is like all, so most of the dust particles that are in the galaxy are all oriented in this around these lines. And this is what we are doing, what we're seeing here. Is like, it looks like that for example, in this case, the spiral galaxy has a strong enough magnetic field, and also very ordered magnetic field that allows most of the particles to be oriented in one specific direction. And you see that most of them are oriented along the spiral arms. And that was like very shocking, because you have a lot of particles there, and a lot of movement, a lot of velocities, different velocities, but it looks like the magnetic field are all following the same as the visible spiral arms. So if we go to a galaxy that is a little bit more complicated, is the one that Alex in this chat is here too, and is working right now. So you can see also a spiral galaxy. But in this case, this spiral galaxy has a companion. So it's interacting with another galaxy at the same time. And you can see that the magnetic field lines here, very close to the center of this massive galaxy, is very well oriented as the other one. But when you go to the outer part, you don't see much of this orientation anymore. So you see that actually the interaction of galaxies may be changing those magnetic fields. too. So you see the lines are not that oriented. So another example, for example, another example is this galaxy here that I show. You remember the galaxy, some of them has these very massive jets that is produced by black holes. In this case, you have this galaxy called Centaurus A. It's a very messy one. So we think that this galaxy is the residual of the interaction of two galaxies. So you have one very big galaxy, is elliptical galaxy, that interact with a spiral galaxy. And what we see here is the remnant of the spiral galaxy that is now like warped and distorted. And you see that the magnetic fields now, they're not that oriented anymore. They're all like distorted and they're all like very messy. So that means that the interaction of galaxies is also messing up with the magnetic fields in galaxies too. And the most interesting one, I think, is these galaxies that have a lot of star formation in the center. So you have a galaxy that is creating a humongous amount of stars in the center. And these stars are expelling matter to the intergalactic medium. And it looks like that is not only expelling matter, as you see here in this picture, but it's also affecting the magnetic field, and you don't have the magnetic field anymore in the galaxy. You have the magnetic field away of the galaxy. So, and it looks like that's like connecting is pushing the magnetic field away and connecting galaxies to each other. So this is like the kind of result that we're seeing here, and this is important because we know, so the galaxy formation is not only affected by gravity, as we always think, but also you have the magnetic field changing the movement of the gas and dust in the galaxy itself. So I think that I can finish more or less here, and if you have questions, I will be very happy to discuss from now on. Yeah.
Wow,
Yeah.
that was great, Enrique. I suppose if you could stop sharing your screen.
Oh yeah.
And then we could feel free to unmute yourselves, but I'll get started with the chats.
Oh.
And while you were talking, there was quite a bit on how beautiful the slides were.
Oh.
and your personal history in one slide, and how Canada is out of the question for you to visit. And then guesses on the galaxy that you were trying to show was the Milky Way. And the Bill Wall in Vancouver right now was wondering, how do you have flight attendants?
No, we don't have flight attendants. No, so we have okay, so we have the 3 pilots, right? And the third pilot is just in case something happened to the one of the 2 main ones, so it can rotate. And then we have 2 safety people, just in case something happened, it's a fire or some major issues, they know exactly what to do, and those are the one that control that the airplane is working correctly. And besides that is all engineers and astronomers working. So no flight attendant neither. So that means we had to bring our own food and our own coffee.
Your own colleague and my old friend Pam Markham thought your demonstration of the stability of the telescope was fantastic. And then there was quite a conversation about the turbulence from the opening in the fuselage. I know when they were developing it, they were not just worried about the turbulence, they were worried about the structural integrity of the aircraft. Having, you're going to take a huge hole out of this aircraft. And I know they were very worried about that. And of course, it had to pass all sorts of commercial airline safety standards.
Yeah.
So So Bill Wall noted that was an excellent question. There must be some restrictions on the specifics of the flight parameters like speed. Is that true?
Yeah, so I would say from my knowledge, and what the pilots say, the pilots don't even notice when the door is closed or open.
Wow.
So they don't know. So you have to tell them that the door is open and closed. But when they're pilot, so doing when they're working with the airplane, so they don't notice it. And so if you can see, I don't know if so the fuselage has some kind of like a bump around the door in order to make it more aerodynamic and to reduce the turbulence going inside of the hole, and also for the turbulence for also reducing the movement of the telescope and reducing the turbulence that go inside of the hole and make it more unstable. So I don't know the whole story because that was years ago and that was before my era. But I think that right now what the pilot says, like they don't notice any vibration or anything with the door open or closed. Yeah.
So it's kind of like a race car with its wings. So also Pam notes that at these longer wavelengths, turbulence poses less of an issue with regard to optical clarity.
Yes. Yeah, so so you have so you have like few turbulence, right? So one is like the whole airplane moving around, right? And this is what the video that I show. So the bulkhead is mechanically absorbing the vibration. So this is one way to reduce the turbulence. The second phase, the second level, is a digital, I would say, like a digital level. So what you do is like you point to one star that you know where is it, and then you make small corrections in order to make the star exactly in the position of the camera that you want to. So that's the second correct, and that's like actively doing it all the time. So this is like it's a person controlling that the telescope is pointing to exactly the same position. We call it the guiding star, and we're guiding to the same position to the same star constantly. So the combination of those two make the difference, made the shift of the stars in the camera to be smaller than the resolution that we have in the camera. Yeah.
You within your wavelength range, your figure of merit is on the order of a few arc seconds. Is that right?
Yes. So so we have from, let's say, in the infrared all the way to the far infrared is between 3 arc seconds to 20 arc seconds.
Okay.
Yeah.
So that's better than anything up in space right now, correct?
For far infrared, yes. Yeah. For far infrared, yes. Yeah. So until the James Webb work between 3 to 20 microns. So then the James Webb will be better in that specific wavelength range. But Sofia go to longer wavelengths, and is no space telescope right now that work in the same wavelength. So we have the base spatial resolution in the far infrared.
So Tom Mikas asks, is there any source of infrared interference?
No, so okay, so that's interesting. So we have one instrument that we call is the Great instrument. It's a German instrument that actually you cannot use the microwave when when the instrument is using it, because because it works as a similar wavelengths. So then the microwave that we have on the airplane interfere with the observations. So it's sensitive. So that's the only instrument that we have that actually we have some interference.
So cold coffee.
Yes. Yes. You don't want to be on those flights because they actually, the German team like to be very cold. They don't like the heat. Also, the instrument doesn't like the heat neither. and you don't have a microwave. So is please don't fly. If you if you are a teacher, don't fly with Greg.
Okay, I'll fly with Hawk Plus. And Tom has another question. Is the autopilot commercial or special?
The autopilot commercial special. I don't know. I think maybe commercial. I don't know. We don't. I don't know. I don't know. If we use autopilot at all. I mean, the pilots have to. You see the flight plan, right? So it's highly demanding, and the pilots need to be correcting the path of the flight of the airplane constantly. Like every 15 or 20 minutes, needs to move it. So if you move a little bit, so it can be small, but after 20 minutes, you are like maybe 100 miles away from where you need to be. So they are constantly moving. Actually, we have two people in the airplane called mission directors. So the mission directors are the people who make sure that the airplane is moving in the right path and also the science is taken correctly. So this is like the interface between the pilots and the scientists, and those people are looking at the screen where you can see the path and where, so the theoretical path where the airplane should be and where the airplane it is correctly. And if they see that changing a little bit, they call, well, they have a direct channel with the pilot and they say, they call it one left, one left. It means that you need to, the pilot need to go and move a little bit, move a little bit, move a little bit. And then they actually every 15 minutes doing that. I mean, it's crazy. So they have to correct it all the time there.
So
Yeah.
they have a reason to be there.
Yes. Yeah.
Richard Lukey from the Gloucester Area Astronomy Club. What must research astronomers do to obtain time on Sophia for their projects? What's the process?
So the process is, so a researcher has an idea first, and then say, okay, for example, I want to observe, yeah, magnetic fields in galaxies. And then what they do is, Sofia open a call for proposal every year. It's a call for the whole international astronomical community. And they say, give me your ideas, write a project. Usually is between 3 to 5 pages, depending of how big the project is. And then write your idea, write as good as you can with all the resources that you have, and then we write it. Yeah, and then we read it. And then what we do is like we accept all the proposals, which are projects of people like, for example, Pam or Alex or me. And then the people at Sofia say, okay, now we get the projects, and what we do is we call experts in the field and everywhere in the US, and then we create this panel that what they do is they read the proposals and they grade the proposals in best science to not best science. So, and then after that, no, because I mean they're all pretty good proposals. You know that it's pretty bad. It's like you have really good proposals. You have 100 something proposals every year, and then they have a very hard time to choose which ones are the best one. For example, we offer more or less 500 hours of observation every year. So this is the amount of hours that Sofia do for the astronomy community, 500 of them, but we receive around almost 2,000 hours. So the astronomy community is asking for more hours that we can give them. So we actually have select the best of the best based on their science. Only science. Know where you are, know who you are, it's no favoritism. It's all pure scientific merit. And then after that, we communicate the researchers that their proposal has been approved, and then we invite them to fly with us, and we give them the data afterwards. I think that basically the process there.
Okay.
Oh yeah, Alex, yeah.
So
Yeah, Alex has a Alex, yeah,
comment. Go ahead,
yeah.
Alex.
No, I was just going to say that I joined Enrique's team very recently. I had absolutely no idea how to observe in fine infrared or anything at all. But the good thing with Sofia is that it's an observatory that it's unique. I mean, it's you don't have anything like that. It's when I think that when you try to write a proposal, one of the most critical things that you have to explain is why do you want to observe with this telescope and not other? Why do you want to observe with Hubble? And if you say with Hubble, I don't know, I can do this with any other telescope on Earth, then they will tell you, okay, then you go to other telescopes. That's it. But if with Sofia, what happens is that you don't have anything like that in space or on the ground. On the ground, it's impossible. And there is no other Sofia flying around. So the thing is, there are many projects that are still to be. Everything is new. The main problem is how to work out science that you don't have a lot of reference. I mean, one of the problems that we have is we are doing things that we don't have previous reference. So it's very risky in terms of science. We may be wrong, but that's something that you need to accept.
Thank you. Bill Wall has had his hand up for quite some time. Would you like to ask a question, Bill?
Yes, I would. I'll also make a comment or two, if I might. First, thanks to Bill Waller for inviting me to join you folks today. The predecessor to Sofia was the Kuiper Airborne Observatory. And when I was a graduate student, I had the opportunity to fly on that a couple of times during 1 week. And while it's exciting in a general sense, it was actually very tedious during the observations and tiring, and I'm sure you can appreciate that. One thing I wanted to say was your demonstration of how the telescope was very stationary or very smoothly moving compared to the vibration of the aircraft. I remember that seeing that on the KAO, where you see this sort of cylindrical type of platform, I guess you could call it, where the telescope was on the other side of it. And the whole aircraft was sort of vibrating around it, and it was moving very smoothly, and it was just fascinating to watch. So I have seen that. But my question is, as I recall during those flights, that sometimes you had to service the instrument during the flight. I don't know if you're able to do that on Sofia. It seems like it would be a good idea to be able to do that because, well, things can change. Is there a way? I suppose there's a way of doing that. You have to basically have like an airlock so that you can get to it.
So usually what we do with Sofia is like we prepare the instruments before we go flight. The service is done right before or after the flight. So every single instrument has been designed to hold the whole flight without any service at all. Service mean, for example, with Hawk, we fill the instrument with liquid helium at 4 Kelvin every day and morning, and then with like 50 liters or something, the liquid helium, and then that holds for 28 hours, and that's perfect because then we do the thing for the day, we fly 10 hours and come back, and the instrument is still working. And that happened with other instruments too.
A lot of careful forethought there, yeah. One other question. These observations of the magnetic fields in galaxies, what are they telling you about galaxy evolution or star formation? Are you able to distinguish between certain physical models, for example?
Alex is laughing. This is like, okay. Yes, it's telling us about galaxy evolution, but the point is like, we don't know yet. The field, at least this field is pretty new. We have the first observation 2 years ago, and we see the signature of it. When you go to the literature, it's a lot of people that have been doing this in radio observations for the past 40 years, and they have traced a similar magnetic field that we see now, and they see the magnetic field at order, that some galaxies are dominated by magnetic fields in the inner bar, that you also have some of the quenching of star formations because you have magnetic fields. But in our case, we are tracing the same magnetic field, but a different part of the galaxy, in a part that is like colder, and in a region that is also denser too.
Better resolution, better spatial resolution, maybe than the radio observation.
No, it's similar. It's similar spatial resolution actually. Both of them, the radio and us, is very similar. Yeah. So then and now we are seeing for the first time, actually Alex is the person who did it, that we see differences between the radio and ours. So that means that perhaps the star formation is changing the magnetic field, or perhaps the interaction with other galaxy is changing the magnetic field. So as I show there, you have the Centaurus A, this galaxy shown with the big jet. The magnetic field is not ordered at all. So, and that galaxy never been observed before. Radio cannot observe it. And then it's only Sofia can do it. So and when I did it last year, I was expecting an ordered field, and you don't see that ordered field. So that is telling you that the galaxy interaction, which is a specific signature of galaxy evolution, is changing the magnetic field. And it's actually making it stronger, which may quench or stop the star formation if the magnetic field is that strong or not. So we still are trying to figure out what is actually telling us.
Thank you.
Yeah, I don't know if Alex wants to add up, because he's the one who is doing all the work now.
I think that you summarize everything way better than he could do, but
so there was a question about how the Sofia gets funded, and I was just wondering whether you Alex or Enrique could comment on that. I know that there's been a history with Sofia, that it was on the chopping block with NASA and Congress for a while, and I don't know what the status is today. I do know that as of the last meeting of the American Astronomical Society, you made quite a splash, and it made the papers and all sorts of other media platforms. So if you could comment on the status of Sofia in terms of its support.
Yeah, I think it's right now it's fully funded, and actually I think it has more funded than they requested. So the Congress give them more money than they requested by the program. The issue here is like you know more than me, because I'm not from the US, so I don't know exactly all the rules here. But you know that you have two different. How I understand it, very naive and outside of American full rules. You have the president budget that they need to be approved or refined later on by Congress. And the president budget for the past few years, they have been trying to remove some astronomical observatories, Sofia included. So then after that budget, what happens is like you have a lot of people doing lobby and talking with congressmen, Congress people, in order to put it on the final budget that the Congress need to add it. So it's a history of the president budget to remove it, but I think that the Congress always fill it up afterwards. Maybe, yeah, William, I don't know if you have a comment on this, or or another OPAM knows more about this. But what I understand right now is fully funded and is up and running, and I think it's a lot of support from the Congress to keep it going all the way from the senior review and the standard mission.
Well, one of its major advantages is that it's supposedly has a 20, 30-year mission lifetime. And so over that period of time, it can accumulate a lot of hours observing.
Yes, yeah. Yeah, and I think like one of the key points here that I think Alex said too is like, and I mentioned in the talk, is like it's very, very, very expensive to send something to space. And whatever you send is all. And so Sofia gives you the best of two worlds. So you can do something very experimental and put an instrument that never been done before. For example, Hawk Plus. It never exists before. And you cannot put a Hawk in space because it has a lot of moving parts, and also have a new technology, and has highly demanded the liquid helium process too. So then you cannot put that in space. If you put it, it will work for like a month or two, and then you spend $1 billion for 2 months of work, which doesn't make any sense. So rather than that, so you can spend $20 million, put it on space, you put it in Sofia, and if something is broken, we can come back, fix it, and then fly next day and perform science. And you have something that is new. The research is completely new, and you can create a lot of highlights there, and you use it as a platform to testing for future space-based missions. For example, there is a call for the next space mission for for NASA, and one of them is called Origins. The Origins is a bigger telescope than Sofia, but has a very similar instrumentation as Sofia, and that's a space-based telescope for the 2030s. So what we can use Sofia to test some of the things that can be put on that space telescope there, for example.
So very good. Looking to the future.
Yeah.
So Enrique, I think we're out of time. I want to thank you so much for being willing to give this presentation, and I'm so glad that some of your colleagues were able to join you.
Yeah, I'm also happy to be around, and I have a blast here. Very, very nice, and also happy that Pam and Alex joined. That's great.
Okay. Well, I'll follow up with the recording, so
right.
You'll get to see yourself again.
All right. Yeah. Excellent. Well, thank you so much, and enjoy the evening in the East Coast.
Okay. Thank you so
All right.
much.
Bye.
Bye.
Bye.